Thank you. Great to be here. So I was asked to spend 10 minutes talking about not our company specifically, but about the space broadly. And as the first speaker in sort of this biochemistry and biology set, I kind of want to set the stage, hopefully, for all of you. So with that, let's see if we can jump into the slides. Wait for it. All right, while the slides are getting set up, I'm going to just share a little bit about the two worlds that I want to tell you about today. So the first world, trying to stall. Does anybody have any good jokes? I'm not much of a joker. Sorry. I think maybe it was too big to load. It's because we have so many images. There it is. Perfect. So stealing from Zavin, who spoke earlier, talking a little bit about radical empiricism and translating that to biology. And in particular, I want to just talk about what I see as the future of biotech and hopefully set the stage for others. So I mentioned these two worlds that coexist somehow. So the first world is the one that all of us live in. This is the world of technology. So since the 1980s, we've seen about a million-fold decrease in storage costs. We've seen a massive increase, exponential increase in compute. And we've seen sort of rules-based expert systems move into machine learning and deep learning. And this affects our lives in so many different ways. But one of the examples I love to think about is this idea of mapping the world. So in the last 30 to 40 years, we've increased the amount of resolution in these images by 100-fold. We've increased the spectral content 100-fold. We used to take a month or a year to image the Earth, and now we do it multiple times every day. And this is giving rise to all sorts of things when you layer machine learning on top. So global data, partnered with Google Maps layers machine learning on top of these images to help you get to your destination, to understand the traffic flows. More recently, companies have sent up satellites that are enabling us to track refugees, track shipping lanes, and the ability to take these massive image-based data sets and layer ML on top of them is giving rise to all kinds of things that are changing our lives. I want to contrast that to this other world that somehow still exists. This is the world of biopharma. So despite having hundreds of thousands or millions of incredible people working really, really hard, it's 10 times more expensive to develop a new drug now than it was in the 1980s. It's about $2 billion per new drug. Meanwhile, there are hundreds of millions of people all around the world living with everything from malaria to rare genetic diseases. And in 2018, in most cases, we actually can't even treat these people. And that just seems absurd, right? There's this massive dichotomy between the world of biology and the world of technology. So why is that? Well, since the 80s, there's been a serial formula in an incredibly conservative industry, and I think Zavin talked a little bit about this earlier, studying one disease at a time with one hypothesis generated by humans. It's almost artisanal. In this massive, massive, complex area that we call biology, we are using this massively reductionist approach. And that means that it takes 10 to 15 years to take any new drug to the market. There are examples of it being shorter and examples of it being longer, but on average, it takes us more than a decade to develop a new drug. And that just seems crazy to me. And in fact, one of the reasons that it's taking longer and costing more to take drugs to patients and improve their lives is that the barrel is being scraped of all of the low-hanging fruit where this reductionist approach to biology works. The diseases that are left are not amenable to a reductionist approach. You need something much more complex, something that embraces the complexity of biology as a system. So what if we could map biology the same way that we're mapping the world? And that's in some ways, how our company got started. So I'm going to talk a little bit about recursion. Apologies to the organizers. So let me share this idea that we're seeing. This is this movement towards radical empiricism. Many experiments, many data sources, many diseases, many treatments at a time, iteratively created alongside machine learning models. And doing this, you create a virtuous cycle, an iterative cycle, whereby you can broadly map biological findings and generate new biological insights, and ultimately achieve the vision, which is to treat every patient where they are quickly with the right treatment for them. So a case study in us, Recursion. So we've built this massive automated laboratory, and in this lab we conduct about 100,000 experiments every week. And from those experiments, we generate about 2 million images. So far, we've captured about a petabyte of images, and we continue to scale this laboratory. By the end of this year, we'll be generating about 7 petabytes of images of human cells per year. And this actually looks a lot like the satellite images we were looking at earlier. Right? So these are human cells, different human cells, under different conditions, different diseases modeled, different drugs applied. And by leveraging computer vision and machine learning, we can extract the information that's in these images to try and understand biology. So what does that look like at a little bit of a deeper level? So we take the billions of images across hundreds of millions of different biological perturbations, and we use deep neural networks and more traditional segmentation and feature extraction methods to represent this data in a high-dimensional representation latent space. So what does that really mean? And I'm the biologist co-founder, so I've had to learn all these things. But what this means is that we can start to do some really incredible things. This is where radical empiricism moves to insights and inference. So at the top, what you actually see, this is hundreds of millions of experiments boiled down to a visualization of this latent space. And what we're doing in the top row is actually predicting the result of an experiment before we actually do it. So we've generated lots of data on a whole bunch of compounds, and we have a new disease model that we've never studied before. And using this massive data set, we can actually predict what drugs are likely to cure this disease, in a dish at least, before we even do the experiment. That's actually pretty profound. You take those 100,000 experiments that we're doing every week, and instead of brute forcing it, as we did when we started, you actually start loading in the predictions before you do the experiment, and you create this virtuous cycle, and you iterate. And when your prediction is right, you're right, which is good. You're getting treatments to patients faster. And when you're wrong, you're enriching the data set around an area where, from a statistical perspective, you didn't have a good prediction. And this goes beyond just the black box of biology, where we can say, hey, we think this drug might work, because it turns out a lot of biopharma companies aren't interested in a guess, right? They want to understand how a drug works. And you can actually map a compound in this latent space to all the other experiments you've ever done. And from that, you can try to understand how a drug works, what side effects it might have, what sort of toxicities it might have. And so this is just an example of our company building this massive data set, bringing other data sets from the public domain in, using machine learning to rapidly iterate, generate hypotheses, test them, and create this virtuous cycle that I think is going to fundamentally disrupt this industry. And there's lots of others. So you'll hear from a couple other companies that I think have a similar approach to biology after me, and we'll be on a panel later. But there's companies all across the space. In human physiology, companies like 23andMe are taking massive data sets of people's DNA, along with questionnaires where they talk about their lifestyle, and they're answering questions about how our genes are related to things like our weight loss, or things like whether or not we like the taste of certain cheeses or some other weird thing like that. But these are just training wheels for the more complex questions that I'm certain they'll be asking. And in the space of clinical trials, you see companies like Flatiron and companies like Science 37 who are taking the clinical trial to where the patient is. So in the case of Science 37, they're doing clinical trials on cell phones. And in the case of Flatiron, they've studied millions of cancer patients so that you can actually do a clinical trial without having a control arm. They just virtualize the control arm from the massive set of data that they've already generated. That takes half the cost out of a clinical trial. These are hundreds of millions of dollars. So it's no wonder that Roche bought them for about $2 billion about a month or two ago. So I hope I've given you, as my time runs out, a brief summary and introduction to this space of biology, this incredibly complex space where I think we're going to see a new generation of companies who are much less conservative, who are building massive data sets and iterating on those data sets to create a virtuous cycle. And I'm incredibly confident that companies like us and like the others you'll hear from in a few minutes are going to bring more treatments to more patients and disrupt lots of other industries with biology in the coming decade. Thanks.